It's my pleasure to introduce Konstantin Tikhomirov, who will be speaking on quantitative invertibility of non-Hermitian random matrices. So during the talk, please, if you feel like asking questions, you really shouldn't. I mean, you shouldn't interrupt him, but you cannot. Do it on Discord, please, and at the end of the talk as well. I yield the floor to Konstantin.
Thank you very much. So let me share the screen. Okay, I hope that you can see my, oh, just 1 second. Okay, so I hope that you can see my presentation. Okay, so let me introduce, so let me start this talk with dedication. This is a dedication to my supervisor at the University of Alberta, Nicole Tomczyk-Jagerman, who passed away very recently. Her main body of work concerns convex geometry, geometric functional analysis, but she also, together with her collaborators, made a number of very important contributions to the random matrix theory. For example, I can mention a result on estimating the sample covariance matrix of log concave distributions. So now let me go to the mathematics. So here's the setup of the problem I'm going to consider. So we have n by n square matrix. The singular spectrum of A is the set of n singular values, which are ordered from the largest to the smallest. So S max here is just the spectral norm of the matrix, and S mean can be viewed as 1 over the spectral norm of the inverse of the matrix. So the condition number is defined as the ratio of the largest and the smallest singular value, or alternatively, it can be just written as the product of the spectral norms of A and A inverse. Now we assume that A is random. I'm going to discuss the models of randomness in a moment. And the goal of the line of research that I'm going to describe is to get upper bounds on the probabilities of this probability that S mean of A is less than some small number epsilon. I must say that partially because of the time restrictions, but also to be able to expand on some specific problems, I will not discuss a very interesting direction of qualitative, I can say, put it in these words, qualitative invertibility, when we're only concerned with estimating the probability that a matrix is singular. And a number of very interesting results have been obtained in this direction. But I will not discuss them because I'm going to discuss something that has motivation coming from numerical analysis, stability of matrix computations, and computing the limiting spectral distribution. And both of these applications require quantitative estimates on the smallest singular value. Another thing that I'm not going to discuss, also very interesting and very active recently, research direction is invertibility of Hermitian random matrices. So I will skip this discussion as well. So now about motivation. So why it can be of any interest to understand the distribution of smallest singular value of a random matrix, and the sort of why the smallest singular value is distinguished among the entire singular spectrum here. So the first thing I want to mention is the relation to computing the limiting spectral distribution. So suppose that we have a sequence of random matrices. So AN here is a sequence, and the matrix AN has dimension n by n. So mu n here denotes the normalized spectral measure of AN. Just we put the weights 1 over n for every eigenvalue on the complex plane. And the general question is this sequence of measure converges to a non-random measure on the complex plane? So the mainstream approach in the case when the matrices are non-Hermitian, mainstream approach to this problem is sometimes called Gurkov's hermitization argument. It is based on this identity, which relates the eigenvalues of the matrix of interest AN with the singular values of the shifted matrices AN minus Z times identity for some parameters Z on the complex plane. So from this formula, it can be shown that the knowledge of the singular spectrum of the shifted matrices allows us to get information about the eigenspectrum of AN. So because we're actually interested in the limit as the size of the matrices grows to infinity, to be able to derive some results about the limiting behavior of eigenspectrum from by knowing some convergence results for the singular spectrum of shifted matrices. For this limiting implication to work, we need some additional regularity condition. So here I wrote the regularity condition. There are some slightly different formulations of this method. So in this condition that I wrote, what is important is, you see, we are taking the summation over all indices corresponding to either very large or very small singular values of the shifted matrices AN minus Z identity. And we sum in the absolute value of the logarithm. We normalize by dividing by n, and then we want this quantity, which is a random quantity, of course, if AN is a random matrix, to be larger than any predefined positive threshold epsilon with probability that goes to 0. That goes to 0 as t, as a parameter t goes to infinity. So thus the argument, hermitization argument, which allows to tell something about the spectrum of non-Hermitian random matrices would work as long as we can say that this condition is satisfied, and this condition is satisfied if there are not too many very large or very small singular values for the matrices AN minus Z identity. So in particular, we want to say that the smallest singular value of this shifted matrix is not really too small. So the second motivation comes from numerical analysis. And here I consider a toy example, really. Maybe if I have a couple of minutes at the end of the talk, I will also consider something more serious. So the toy example here is about solving the system of linear equations AX equals B. Suppose that the vector B is perturbed by some small vector delta. And we want to understand what is the relative distance between the solution of the perturbed system and the solution of the original system. So the relative distance here is the ratio of the Euclidean norm of x minus y and the Euclidean norm of x. So then simple computation gives that this can be bounded from above by the condition number of the coefficient matrix A times the relative error of the coefficient vector. So we take perturbation and divide by the Euclidean norm of the original vector B. So if the condition number of the matrix is small, we can say that the relative error is small. So the system is stable with respect to perturbations of the coefficient vector. So having small condition number is good. So this is a connection between probability and numerical analysis. So suppose we want to understand for some class of computational problems if or to justify why the certain matrix computations are stable in practice. So not affected too much, say, by doing floating point computations instead of exact arithmetic. So the way to justify these things is to model a typical matrix for a given class of computational problems by random matrix. So as a simplest model here, we can take matrix with IID standard Gaussian entries. It can be IID entries, say, uniformly distributed on in the interval 0, 1 or -1, 1. And if I'm not mistaken, such models are actually used as a benchmark for testing matrix computation algorithms. So here are some more models of randomness, which are popular in the literature. So here we have matrix A with IID ±1 symmetric entries, or we can consider the matrix A with IID Bernoulli P entries. These two models are sort of the first choice if we want to understand the behavior of discrete random matrices in certain context. So another thing of interest can be sparse unstructured matrices. So if we want to understand what happens if the matrix has many zeros and really no predefined pattern of non-zero elements, we can model this matrix by taking IID entries as before, but this time every entry is going to be the product of a Bernoulli P random variable for a small parameter P, which is supposed to tend to 0 when the dimension grows to infinity, and some independent random variable Xi. So I'm going to discuss or mention very briefly some results for these models. Okay, so here is basically a summary of this part concerning numerical analysis, why studying invertibility is of importance. So we want to say that for our model of randomness, probability that the condition number is large is close to 0. This would guarantee stability of certain matrix computations for this model. So because for many models, estimating the largest singular value of A is relatively simple, or at least the methods for doing that are well established. The main issue when estimating the condition number is to control the smallest singular value of A. That's why we come up with this problem. Okay. So next, let me check the time. Okay. So next, I want to mention some what I call here well-established results on matrix invertibility. Of course, the list of results is so extensive that I won't be able to mention any good amount of them. So I chose 3 results here. So 2 on this page, and the next one will be on the next page. So the result of Edelman from 1980s concerns the standard Gaussian matrix. So he actually derived much sharper estimates, but in this context that I'm discussing here, the estimate that I wrote here is already very good. So if we have a standard Gaussian matrix, means entries are IID, no symmetry constraint, independent, identically distributed, standard Gaussian entries, probability that S mean of A is less than T over square root n is less than some universal constant times T for any choice of the parameter T bigger than T. The second result I'm mentioning here is due to Rudolphson and Vershinin, but here, as you see, I made a remark that there were earlier results, in particular by Tao and Wu, and also by Rudolphson. So the result of Rudolphson-Vershinian tells the following. So if A has independent, identically distributed entries of zero mean unit variance and bounded sub-Gaussian moment, here I don't describe what it actually means, but let me just say that it means that the tails of the distributions of the entries decay very fast, going to infinity. So in particular, all moments are finite. So in this case, probability that the smallest singular value of A is less than t over square root n is less than constant times t, constant here allowed to depend on the sub-Gaussian moment, plus c tilde to the power n. So if we compare this estimate to the result of Edelman, what is the difference? The difference is this additive term, tilde c to the power n. Tilde c here is strictly less than 1, so this additive term is exponentially small in the dimension n. And by considering discrete random matrices, say the ones with symmetric plus minus 1 entries, it is clear that this additive term cannot be completely removed. For example, if we take the matrix with IID plus minus 1 entries, then the probability that it is singular, so the smallest singular value is equal to 0, is at least the probability that the two rows or two columns of the matrix are the same, or the same up to a sign. And this gives an estimate, some quantity of order n squared times 2 to the minus n. So really, this additive term for discrete random matrices cannot be removed. So the third result, rather it's a combination of a few results, concerns sparse matrices, which I'm going to briefly consider a bit later as well. So here I take the parameter p between n to the minus 1 plus epsilon for any fixed positive constant epsilon and 1. So okay, I should write here 1/2 to be precise, to allow for some randomness. So assume that A has IID entries equidistributed with this product, Bernoulli P variable times independent variable xi, which is say sub-Gaussian with the second moment equal to 1. So this is the model of sparse matrices I mentioned before, unstructured sparse matrices with many zeros. Then probability that the smallest singular value of A is less than square root P over n. And here I should write times t. I forgot to multiply by t here in the brackets. So this probability is less than ct plus the additive term, which in this case is exponent to the minus some constant times p for any choice of parameter t bigger than 0. So we have the linear decay term, and then we have additive term, and it can also be checked that this additive term is not removable and that the quantity in the exponent, this quantity of order Pn, in general is the best possible, as long as we're not concerned with the precise value of the constant C tilde. This is the best possible, which can be checked by considering, say, a matrix with Bernoulli P entries, with IID Bernoulli P entries. Okay, so the next subject I want to discuss is about methodology. So I'm going to discuss some what can be called standard methodology of random matrix, non-asymptotic random matrix theory, something that already existed, say, 10 years ago. And then I'm going to consider some novel additions made in the past few years. Not all of them, but just some selected ones. So let's see. The smallest singular value can be written in this form as the infimum over all unit vectors x of the Euclidean norm of the matrix vector product AX. So now the study of the smallest singular value can be based on this formula. In order to proceed, we will need to develop three elements: partitioning and discretization of the Euclidean sphere, invertibility via distance, I'm going to discuss what it means exactly, and anti-concentration of random linear combinations. For that, I unfortunately won't have time. I will only briefly mention what this means. So, okay, let's see. First, partitioning and discretization. So we have the Euclidean sphere, which we split into compressible and incompressible vectors. This terminology is taken from the paper of Rudolfsson-Verschin I mentioned before. Compressible vectors can be defined as the vectors on the unit sphere whose Euclidean distance to n over 100 sparse vectors is less than or equal to 1 over 100. The constant that I chose here is arbitrary. It's supposed to be just some small constant. N over 100 sparse vectors, by the way, are vectors having at most n over 100 non-zero components. So compressible vectors, you can view them as vectors close to sparse. And that's why they are represented like this here. So I wanted to make an impression that these vectors are close to the standard unit basis vectors. So, and incompressible vectors, which is the complement. So the set of incompressible vectors actually needs some careful partitioning, which I will not discuss here. So there should be partitioning into about n of by the order of magnitude subsets, and a different treatment of these subsets is required depending on the structure of the vectors constituting them. So why this partitioning is of any interest in the context of this problem? So we start with the quantity we want to estimate, probability that S min of A is less than tau for some parameter tau. Then we can trivially write that this is less than probability that the infimum over compressible vectors of the product AX less than tau plus probability that the infimum over incompressible vectors is less than tau. So now we can treat these probabilities separately. So for compressible part, what can we do? Because the compressible vectors are close to sparse, in some sense, there are very few compressible vectors on the sphere. So how this notion can be made rigorous? It can be checked that one can define a discrete subset, which is denoted by calligraphic n here, discrete subset of the set of compressible vectors, such that with high probability, the infimum over the compressible vectors x of Euclidean norm of AX is approximately the same as the minimum over all x and the net in this discretization of the Euclidean norm AX. So we replace the set with continuum number of points with a discrete set with finite number of points. So there is a discrete subset satisfying on the one hand this condition, on the other hand this subset is not too large, so it has some not very large number of elements. So once we have this condition, we can write that the infimum over compressible vectors can be replaced with the minimum, and then the union bound argument gives this relation that I wrote as the last formula on this page. It is imprecise. I try to avoid all the technical details. So what is important here? The quantity we want to estimate can be bounded by the sum over all vectors on the discretization of the probability that the Euclidean norm of AY is less than some constant times tau. So here we need to balance two properties of the discretization. On the one hand, it should be large enough to guarantee that the infimum over compressible vectors is roughly the same as the infimum over the vectors on the discretization with high probability. On the one hand, we cannot make the set too large, because if we do that, then the number of terms in the sum will be too huge, and this upper estimate will be meaningless. So we need to keep the number of elements in the discretization small, while at the same time guaranteeing that this relation is satisfied. Here is the remark that I want to make about the sparse matrices for when treating the corresponding problem of quantitative invertibility of sparse matrices, say the result that I mentioned before, the set of compressible vectors actually needs to be further partitioned according to the size of essential support of a vector. I'm not going into details here because I really don't have time for this, but I just want to give some general idea of what's happening. So for sparse matrices, a finer partition of the set of compressible vectors is needed. Here I just use some terminology from the literature. If you look at the literature on sparse random matrices, invertibility, you will see the notions of dominated vectors, steep vectors, and flat vectors, probably some others. Okay, so now I go to the second methodological element that I mentioned, invertibility via distance, what it means. So far, I only discussed how to treat the infimum over compressible vectors. The question is what to do with this probability, infimum over incompressible vectors. So here I wrote a statement, which I again take from that paper of Rudelsson and Vershinin, so this inequality holds under very general assumptions on the matrix A. And it, as you can see, it relates the infimum, the distribution of the infimum over incompressible vectors, to the distribution of the distances between the columns of A and linear spans of the other columns. So here I have the distance between i's column and the span of all columns except for the i's. So this distance can be alternatively written as the absolute value of the inner product of the i's column and the unit vector yi orthogonal to the linear span of other columns of A. So at this moment, how we can understand the distribution of this quantity. So here is where the third element comes into play, distribution of random linear combinations. So this object, you can really expand it and you can write it as a summation, say j from, or k from 1 to n, k's component of the i's column of A times k's component of the vector yi. And then what you can do, you can, for example, condition on a typical realization of the vector yi, and then study this quantity with respect to the randomness of the i's column of A only. This way, you will arrive into the problem how to understand the distribution of the linear combinations of independent random variables. And there is a huge literature about that. There is a whole theory that was developed at some point called inverse Littlewood-Offord theory. There are lots of classical results as well as some very recent results in this direction. Fortunately, I don't have time to mention this. It is an interesting subject and the key element in the estimation process. So, okay. Now, I'm going to consider some recent additions to methodology. So the three elements that I mentioned so far, partitioning and discretization of the unit sphere, invertibility via distance, and studying the linear combinations of independent random variables. So these three elements together give the results which I mentioned before, results due to Rudelsson-Vershinin, the results on the sparse matrices. It does not concern, by the way, the result of Edelman, which is obtained by a completely different method, relying on the fact that for the Gaussian random matrix, there is an explicit formula for the joint distribution of its singular values. So, okay, so let's return to these methodological elements. in past few years, there have been some progress on understanding invertibility of structured square random matrices. So what is meant by structured here? The entries say still assumed to be mutually independent. Let's consider only this model in this talk, but they don't have to be identically distributed. In fact, some of the entries don't even have to be random. They can be just fixed numbers, or they can be zeros. And then on some prescribed positions, we will have elements with prescribed distributions. So what is known in this direction? So first of all, this direction can be interesting from the viewpoint of numerical analysis, because this way we can model structured matrices. In some computational problems, we're dealing with matrices with certain structural features. There can be some blocks or some band structure, and say explaining stability of matrix computations, for example, by modeling such matrices using IID entries is really not satisfactory. So what is known in this setting? So there are I mentioned here two results. I will mention one more a bit later. So these two results due to Rodolfson and Zeytouni and due to Cook. These results show that under certain assumptions on the matrix, which can be called expansion-like property, strong invertibility results are known. So expansion-like property here means that very roughly, that whenever you take a small subset of columns, the number of columns in this subset is going to be much smaller than the number of random elements in this subset. So roughly speaking, it's not only that each column has many random elements, but also these positions of random elements really do not overlap too much for different columns. So this can be related to some expansion properties of graphs from the graph theory literature. Another addition to the theory is adding some sort of extra randomness to construct better discretizations of the sphere. Actually, this was one of the obstacles in sharpening the theorems that I mentioned before. Sharpening in which sense? In the sense of improving the estimate of the error, of the additive error term, both in the dense regime and in the sparse regime. So here I just mentioned two terms from the literature. Randomized rounding is a standard saying in computer science literature, but it has been used in the non-asymptotic random matrix theory context relatively recently. There is also this term inversion of randomness, or can be called also as some form of double counting argument. So very roughly, the idea of this inversion of randomness is to construct a discretization of certain subset of the sphere by choosing the points in this subset in a random fashion. This allows to get some much better estimates on the random linear combinations, much better estimates on the distribution, and this propagates to sharper bounds for the smallest singular values of matrices. Here I mentioned some works in this direction. I will state explicitly some of the results in a moment. So here is the example of the results that are obtained as a part of this advances in methodology. So here is the first theorem I mentioned here is concerns the matrix with ID plus minus 1 entries. So for any positive constant epsilon, the smallest singular value of such matrix can be estimated in this way. So here, the linear term is just the same as in Rodolfson-Vershinin theorem. There is no really any change. The change comes here. The additive error term, as you can see, is up to this constant multiple is 1/2 plus epsilon to the n. And as I mentioned before, this error term really cannot be less than 1/2 to the n. So it can be argued that up to that asymptotically this is the best possible choice of the additive term. Another theorem concerns sparse matrices. So I consider here the model where A has IAD Bernoulli P entries, P less than 1/2. There is no lower bound. P is allowed to depend on n and can decay to 0 as n grows to infinity. So here is the probability that S mean of A is less than t is less than some polynomial in n times t plus 1 plus little of 1 times probability that A has 0 row column. So here in this case, the additive error term is even sharper than in the previous theorem. It is optimal up to this 1 plus little of 1 multiple. So I must say that the results I quote here. For example, for the second one, the better estimates are actually known depending on the range of P. For example, in this paper by Jane, Sa, and Sony, the dependence here, the dependence of the term involving T on the parameter is much better. But I just want to give some general understanding of what type of results have been obtained without really trying to get the best and the sharpest possible formulations. Another important thing to know, again, is that I'm only discussing here the results about quantitative invertibility involving the estimates on the smallest singular value, and I do not consider very interesting research direction about estimating probability that a matrix, a discrete, say, random matrix, is singular. Okay, so the last addition I want to discuss is concerns invertibility of matrices of this form, A minus Z identity, and this is important, as I mentioned before, in the context of studying the limit in spectral distribution, when the parameter Z is not equal to 0, and when the matrix A is very sparse, or has very sparse and has many 0 rows and columns. So what is the problem with this model compared to the previous ones, to the sparse model discussed before, for example? So when we consider, say, Bernoulli P IID entries for our matrix A, when the parameter P is less than log n over n, we start having 0 rows and columns in our matrix with high probability. And what this means is that some rows and columns simply don't have any randomness. There are no elements, say, except for the diagonal elements for the shifted matrix. So this really requires some special treatment of the rows and columns, which, apart from the diagonal entries, contain only zeros. And to do that, some additional graph structure related to the matrix have been developed in this work and allowed to get some bounds which are sufficient, not very strong, but still sufficient for estimating the limiting spectral distribution for this very sparse model. Okay, so I have only 2 minutes left. So let me just say about the open directions. So one open problem that I want to mention is about structured random matrices. Say, suppose that we consider the model where the entries are mutually independent, psi ij are IAD, and then we just multiply them by the indicator that the pair ij belongs to some predefined fixed subset of indices T. And we want to understand how to estimate probability that S mean of the shifted matrix A minus Z identity is small, depending on the structure of T, whether we can get this good bound at all. So T can be viewed as a subset that encodes the variance profile of this matrix, and estimates of this type are important in connection with the study of the limiting spectral distribution of inhomogeneous random matrices. So some partial results exist. So as I mentioned before, if T possesses some expansion-like properties, some results have been obtained. A recent result deals with block band profile. Here I tried to draw the picture of how it looks. So here there are blocks, these blocks, small squares, which contain IAD elements. Everything outside of the blocks is 0. And for this model, in some range of parameters, the size of the block, the very good estimates on the smallest singular value were obtained. Okay, so another question is concerns with stability of the Gaussian elimination, and unfortunately I don't have time to discuss it. Let me just say, I think it's a proper remark that a number of milestone results in the random matrix theory have been obtained in present-day Ukraine, and definitely it is a wish that the Ukrainian mathematical school will overcome current disasters and will be even stronger in the future. Thank you for the attention.
Well, I can clap. Thank you very much. And further questions will have to be done, to be posed on Discord. But thank you for this wonderful talk.
Thank you.